last year while I was still at Yale. And here are the references if you'd like to read more about it. I should double check, thumbs up if you can hear me properly, everything. Okay, great. Okay, so today I'll talk about theory of Bloch oscillations, which I'll explain a bit more, in transmon qubits, which I'll explain more for those who aren't familiar with those. And so, of course, my slides will click. There we go. So first of all, just to acknowledge my collaborators in this work. At Yale, I was working with Professor Leonid Glasman and his two students at the time, Vlad, who graduated and moved on to Google, and Max, who was an exchange student from Heidelberg. And coincidentally, we were working with a lot of dialogue with experimental colleagues here in Maryland. Unfortunately, they left here before I got to get here. So Roman Kuzmin, who's now professor at Wisconsin-Madison, and Vladimir Cherian, who's now at the EPFL. So a lot of credit goes out to them. And on the menu today is the first part will be a general introduction to circuit quantum electrodynamics to those of you who have not had a chance to work on these systems. And then the two substantive parts of my talk, we'll talk about this particular system of resistively shunted transmon qubits and this phenomena they can host that's called Bloch oscillations. And time permitting, when we get to the second part, we'll talk more about some weak, strong and weak dualities that these systems host. So let's begin. I usually, when I give seminars, I'd like to think that people listening would have learned something. So by all means, if you have any questions, feel free to interrupt me. I'm not sure I can hear you guys all too well, so you might have to raise your voice. And so why do we care about circuit electrodynamics to begin with? So the catchphrase people will use is that it's an exciting platform to study many-body and strictly coupled light-matter interactions. And so you can start to enumerate the features of it, and they sort of include in ascending order of buzziness. So you can use it to implement your favorite models from condensed matter theory. If you ever wanted a system that gives you like a clean Luttinger liquid, right? That's interesting. Or you can explore AMO physics with customizable, designer-made atoms. That already starts to sound a bit more sexy. Or you can realize, as I said, strong coupling electrodynamics if you're not happy with the weak coupling of vanilla QED. Or you can make hardware for quantum computing and make a lot of money, right? So that's the ultimate buzzword. And so to give you an illustration, so I was around this time last year, I was walking around London. As we said, I did my grad school in Cambridge. I wanted to graduate, and I happened to see this sign outside of an optician, right, that says, "Here, the modern spectacle maker." And I realized, obviously, there's a typo in here. The sign should say qubits. Okay, so moving on, we can compare, by various features, what I call vanilla quantum electrodynamics in the vacuum to cavity or circuit QED. So in both, so in one case, the medium is the vacuum, and in the other, for the purposes of this talk, will be a superconducting circuit, and I will explain how that works. And in both cases, light is just carried around by photons. However, where they start to differ is in matter. So in regular AMOP, your matter is atoms and ions. In circuit QED, your matter is composed of Josephson junctions, which we'll get to in a second. Now, both theories have, an energy scale that for you is infinite energy, and you want to work below that, right? So in the vacuum, it's polarizing the vacuum to create electrons and positrons, yada, yada. Scale is about 1 MeV, right? So you'd like to work below that. In these superconducting circuits, the scale is basically the gap energy of the superconductor. You don't want to create quasi-particles. So for us, all the physics here is well below half MeV. There's another energy scale, which is the qubit energy scale, which you want to avoid in the sense of you don't want noise, but you don't want to learn how to control. And so in quantum information systems that encode it in neutral atoms or ions, this is usually an atomic fine structure transition. So the energy scale is like micro EV. In circuit QED, this will be what we call the plasma frequency. Funny enough, also on the scale of 1 micro EV. So in a sense, the trickiness of working with circuit QED comes from the fact that these two numbers are much closer to each other than these two numbers. And then there's the coupling strength of the electrodynamics. In the vacuum, it's the fine structure constant 1/137. In circuit QED, depending on how you design your circuit, you can cook up a tunable coupling constant, which can range from effectively 0 to something that meets or even exceeds 1 in the correct units. So this is how we realize those strongly coupled systems. And so the basic understanding of circuit QED is the LC resonator that we all remember from freshman year. We can write down the Lagrangian for the circuit in terms of kinetic energy minus potential energy. The kinetic energy is the current passing through the inductor, and the potential energy is the charging energy of the capacitor. So from this, you can derive equations of motion, but the thing that you don't really give much thought to before is that the conjugate coordinates here is the charge Q, and what turns out to be the flux that passes through the inductor. So going forward, we remember that the conjugate quantities in this universe are charge and flux. And if you complete the Legendre transformation, you can get the classical Hamiltonian for these 2 degrees of freedom with a Poisson bracket that's 1. Now, the big idea of circuit QED is to realize that even though this circuit could be a macroscopic object, as you can see with your naked eye, you still quantize its Hamiltonian by taking this Poisson bracket to be now a commutator equaling IH bar of quantum mechanical operators. And so this Hamiltonian is quadratic in both fields, and so it's a harmonic oscillator. Naturally, you get this familiar Hamiltonian, A dagger A, and this plasma frequency I mentioned before is basically the resonance frequency of this LC circuit, frequency 1 over square root LC. Now, we want to work in quantum mechanical systems, and so decoherence is bad. This means that up until this point, I didn't really mention what conductor these guys are made of. The reason we use superconductors is less with the fact that they're actually superconducting. We don't need supercurrent per se, but just we don't want to induce any sort of decoherence that would arise if these were just, copper. But it does mean, working with superconductors, that there's a natural scale to measure both charge and flux. Right? So we can measure flux in units of 2e, the charge of a Cooper pair. So n will count us the number of Cooper pairs. And we can measure flux in terms of the superconducting flux quantum, right? H over 2e. And if you divide it by this flux quantum, then you get a dimensionless measurement of flux. And so we can bring this Hamiltonian to a sort of natural dimensional form of charging energy and inductive energy of these 2 variables, which are canonically conjugate. Now, I said that n is the Cooper pair number. And if you think about it for a second, you realize that this phi actually exactly corresponds to the superconducting phase of the superconducting wire. And so, right, usually when you construct BCS theory, you take the phase of the superconductor as a parameter. But now, actually, again, we've promoted large macroscopic objects into a quantum mechanical operator. And so now the phase becomes an operator. So this so far is a linear system. It's harmonic. And interesting physics doesn't arise from a harmonic system. So instead, let's go to the next level, which is the most simple anharmonic system. And for this, we go to Josephson junctions. And for the sake of this description, you can think of a Josephson junction as a nonlinear inductor. So we've replaced the quadratic dependence of the phase by this cosine dependence. And so what this means is that this potential is weaker the larger phi is. And so instead of having the uniform level spacing of a harmonic oscillator, we'll get a non-uniform level spacing. Right? So I can have these 2 Josephson junctions, and they will have the eigenspectrum that kind of densifies as you go up. This is important in quantum information context because this means that if you try to drive transitions between these states, they become what we call addressable. You can try to resonantly excite one to the other, and because the spacing is non-uniform, you don't accidentally induce transitions between other pairs of states. That's why people use Josephson junctions everywhere in superconducting qubits. On the other hand, I can also use a Josephson junction as a coupler between these 2 artificial atoms, or you could call it even the medium in which they interact. And the point is that I can engineer a strong interaction between these atoms and this medium, or between each other, depending on the parameters I tune of this intermediary Josephson junction. And the way to see this is, if I take the energy of the Josephson junction And now the phase difference across this junction is precisely the difference between the phase of this guy and the phase of this guy. And I divide it by the typical energy spacing here. And I use the quantization of, this is a coordinate quantized in terms of A and A dagger. You find that the interaction I induce between the two sides is proportional to this ratio of Z. Z is the mode impedance. If you have an LC circuit, besides a resonance frequency, it also has a mode impedance given by the square root L over C. And RQ, which is a fundamental constant, the resistance quantum, this H bar, H squared over 4E squared, about 7 kilo ohms. Or, this is 1/4 of the von Kiltzing constant if you do quantum Hall. And depending on how I tune this mode impedance, I could be either very close to 0 or have a very large ratio, determining the strength of the interactions. So you can actually draw an analogy to the fine structure constant vacuum QED. And I can express this quantity in terms of the impedance of the vacuum divided by this RQ. And the vacuum, if you didn't know, has a relatively low impedance of 400 ohms. It's very far from 7 kilo ohms, and that's the origin of the weak coupling in a regular QED. And so now we'd like to explore systems where we take this medium impedance to be very large. Now, one thing to realize once we've upgraded these degrees of freedom to be operators is now they have quantum fluctuations. So suppose I shunt this junction with some resistance R. You can run through the calculations and you find that the ratio between the fluctuations of phase to the fluctuations of charge is the squared ratio of resistance to resistance quantum. And this means that if I have a very large resistance, the phase fluctuates very strongly. But now, a very fluctuating phase sounds like a loss of phase coherence if you can't definitively say what it is. And if you've lost phase coherence, then can you really superconduct? That's the basic question. And so an analogy here would be to think of phi as the coordinate of a particle, which now sits in this cosine potential. Now, classically, it can just sit at the bottom of this potential and maintain phase coherence, right? But as soon as I switch on quantum mechanics, it can now also tunnel between successive minims. So even though it's in a relatively deep potential, you expect it to completely delocalize if you wait long enough, right? The ground state of a particle on a lattice is to delocalize. And the only thing that could prevent this in this case is friction. This is what the resistance provides that gives you an obstacle for the motion of phi. And if you crunch through these calculations more carefully, you'll find that there's a phase transition. Because it's induced by the value of the resistance, we call it dissipative phase transition, which was worked out by these guys, Schmidt and Bulgakov. And what it says is, if this shunting resistance is smaller than RQ, the phase can stay localized, and the junction still behaves as a superconductor. That's great. Or if the resistance is bigger than resistance quantum, then the friction is not large enough. The phase will start to tunnel around. You lose phase coherence, and the junction becomes just perfectly insulating. Okay. And the regime we'd like to explore in this talk is actually when we're above this critical point. Any questions so far? All right. So I can give you a sketch proof of why this transition happens, which is suppose I have this system and at some steady state, and one Cooper pair tunnels across the junction. It has to end up on one of the plates of the capacitor, which means that if a single Cooper tunnels through, I have to pay the charging energy of the capacitor. Now, Josephson junctions are pretty small, so their capacitance is small, and so this energy could be quite large. And so the only way I can just increase the system's energy by this amount if I can do it fast enough to avoid the energy time uncertainty principle. However, the minimum amount of time I have to stay in this state is the time it will take the Cooper pair now to relax back to the other side of the capacitor when it discharges through the resistor. So the time that it will take is the RC constant of the circuit. And so the product of time and energy has the capacitance cancel out. And what you find is that the universe doesn't notice that you violate uncertainty if the resistance is below resistance quantum. And so this sort of indicates to you that it's this phenomena, by the way, it's called Coulomb blockade, that motivates this phase transition. Now, the far in the middle moral of the story here is that the competition is between quantum fluctuation and the fact that the charge is discrete. And this is kind of separate from charge being quantum. So discreteness can also arise classically. So that's the true competition here. Now, whether this transition can be observed in practice is actually very actively debated. So this is just some of the papers that came across in the last few years while we were preparing this work. And the reason for this argument comes down to two issues. The first one is that this is a quantum phase transition. You achieve it by tuning a parameter, not temperature. And this means that you get a critical behavior on two sides of the transition only in the limit that the energy you use to probe the system goes to zero. This means that you need temperature to be zero. If you want to probe whether it conducts or not, you have to probe it with voltages and currents to go to zero. And if you want to examine the dynamics of the system, you have to look at dynamics at frequencies also approaching zero. And all of these in a real experiment would not be, strictly speaking, zero. And so they kind of smear out the phase transition. The second issue is that actually achieving this transition point, so just realizing a value of this ambient resistance on the order of the resistance quantum, is both difficult experimentally and also kind of difficult to approach theoretically, because you know how to think about weak interactions, you know how to think about ultra strong interactions, but this regime of interactions being coupling of order one is actually the hardest to disentangle. And so the gist of the research we had done and I'll present today is that the behavior at these relatively large DC bias, so voltage and currents, is actually related to the physics occurring at high frequency. And this means you can probe both of them experimentally in this complementary way in a variety of different experiments. So you could either apply a current and measure the voltage. That's like a DC to DC experiment. You can apply a current and measure at photons. That's basically DC to AC, to high frequency. Or you can do the inverse experiment. You can apply photons and measure current. And all of these quantities are actually interconnected. And what connects them is this phenomenon of Bloch oscillations. So let's now dive into the meat part of the talk. What are these Bloch oscillations in superconducting qubits, and specifically transmons? So suppose I take my junction and I bias it with some current I. Now, classically, it's very easy to solve for the state of the system. We know Josephson's relation, right? The current is proportional to the sign of the phase. So the phase will take on this value, and the equations of motion are solved. Quantum mechanically, this is not so easy because I had to consider the fluctuations of the system. And in particular, as I said, the issue is that charge is discrete. And the charge discreteness corresponds exactly to phase periodicity, right? This is like saying position periodicity corresponds to momentum discreteness, right? And quantum mechanically, if you have a system that's periodic, then its states form Bloch states and form Bloch bands in momentum space, right? So here you can think of this Josephson cosine potential, and the phase can end up in bound states inside every minima, but there will be some hopping matrix elements for the phase to jump between these successive minimas. And quantum mechanically, you'll get complete delocalization across all minimas. So you can run through the motions and you can draw a Brillouin zone for your Josephson junction, where now the momentum is, like we said, what's conjugate to phase, it's charge. So here the momentum label is charge. And as you see, it's discretized over now quantas of 2e, the Cooper pair charge. Now, I can now do semi-classics. So having taken care of quantum mechanics to the level of forming bands, we can do the semi-classical equations of motion on these bands. And so the charge naturally changes by the current, and the phase changes by the group velocity derivative of energy by momentum. And what you'll find, if I have a wave packet at a certain number of charge, and I apply current, it'll accelerate, an increasing charge, hit the end of the Brillouin zone, wrap around, or undergo Umklapp scattering, and come back around. And so it'll complete a revolution. And this cycling motion is what we call the Bloch oscillation. And if you solve these classical equations of motion, what you find is that the phase will also oscillate, but the amplitudes of the oscillation go down the faster these revolutions are. And so you get a dynamical localization of the phase if you bias it with current. And so this allows you to sidestep the fact that the phase becomes delocalized. Now, the issue now to get the high impedance I was talking about earlier is, one, I would like to achieve it experimentally at all. Second, I would like to do that without actually generating heat, because if you just put a big resistor on a chip, it's going to heat your superconductor, and that's bad. And the second problem is, how do I actually describe this resistance quantum mechanically? Right? If everything is classical, I can just write Kirchhoff's laws with a resistor, and that's fine. But we don't know how to do that quantum mechanically. And so the answer to this is an element called a superinductor. Basically, it's an array of very large Josephson junctions arranged linearly, where it behaves like a transmission line, but the fact that you use Josephson junctions instead of the geometric inductance of a coaxial cable means that it basically acts like a waveguide, but the characteristic impedance of the waveguide is typically much larger, and you can meet or even exceed this resistance quantum depending on the parameters of these junctions. So for now, we can forget about how this is realized and just take effectively that there's a transmission line with this characteristic impedance. Now, the neat part is that this realization in terms of a characteristic impedance transmission line naturally gives us a Hamiltonian description of friction, because here friction or resistance takes a form of photons getting shed into the transmission line, and that's where the energy ends up. So you can think of it by analogy that suppose my particle is this bead, which is elastic, so it wants to be a narrow part of this rod, and the rod has like this cosine profile, and the friction is like a rope attached to this bead. So if this bead moves up and down, it will generate waves in the rope that will take away energy. And we can actually just write down the Hamiltonian of this transmission line. And when we integrate out this Hamiltonian, that's how we will get dissipation. And before I tease that you can engineer Lottinger liquid, this is what I meant, that by just relabeling the characters in this expression, you get the Lottinger liquid Hamiltonian. Ta-da! And so going forward, we would realize in the Lottinger liquid language, here, theta is the charge density. So gradient of charge is gradient of voltage, which is the electric field. And phi is flux, and gradient of phi is a magnetic field. And so just to remember now that I'm going to switch to the traditional letter theta, but theta is charge. So it's measured in terms of electric charge. And so now we're going to focus specifically on transmon junctions. And so a transmon is a fancy word for saying I'm looking at a junction where the junction energy is much larger than the charging energy. But besides that, it's just a Josephson junction. And the reason we look at them is because in transmons, you get a very wide band gap between these Bloch bands in momentum space, which is very large compared to a narrow bandwidth of the lowest band. What this means is that there's a very large frequency range for these oscillations to occur that won't excite transitions to the next band. And this just means we can forget about all the bands except the lowest one. And we can make this adiabatic approximation that now the charge on the capacitor is not just the charge on the junction, but also whatever arrives from the bias. But if the system is fast enough to react to it, we can actually now integrate out the junction. And so our effective Hamiltonian is just this cosine profile evaluated at the time-dependent momentum. What is this time-dependent momentum? It's exactly the charge that left via the resistor minus the charge that was injected by the bias current. So to summarize, the model Hamiltonian we'll consider now is this, all these harmonic photons, and the way they're coupled is through this one cosine term that's driven by a bias current. You can also give a name to this model, and you might recognize that this is a sine-Gordon model with two distinctions, that this is a boundary sine-Gordon. So the sine interaction only occurs at the boundary of the transmission line medium, where it's attached to the junction, and it's also driven by the external bias. And so what's neat here is that we can also draw comparisons between this quantum description of a biased transmon and a classical Josephson junction. So usually we think about Josephson junctions in terms of the phase across them. And this transmon, I'd argue, is sort of dual to a junction, and we typically think of the charge across the quantized transmon. And so the energy depends in a Josephson junction, with a sinusoidally on phase, and now depends sinusoidally on charge. The Josephson relation in a regular junction is current equals to dE by d phi, which is sine phi. And now we find that the voltage is dE by dN is sine n. The conjugate relation, right, which I always found very unintuitive in a Josephson junction, is that the voltage is phi dot. Right? And in this case, it's actually quite trivial. It means that the current is the charge by d time. That makes much more sense to me. And finally, if you look at these two equations together, you realize that the Josephson junction supports this AC Josephson effect, which means that if I apply a DC bias voltage to a Josephson junction, it means that phi has to increase linearly in time. It means that the argument of the sine increases linearly in time, and so the current will fluctuate with an alternating component. And in our device, which is dual to that, we find the exact opposite. If I now bias it with a DC current, this leads to a linearly increasing charge, which then gives a AC component to the voltage. So we can now wonder, what are the characteristics of this device? So again, I'd like to appeal to classical physics. And again, if we forget about quantization, just the equations of motion of this Hamiltonian would be that the voltage across the resistor needs to be the voltage across the junction, right? Simple. And it's expressed in terms of this equation. And we see that it has just two regimes. If the current, which is proportional to this frequency, is small enough, smaller than this coefficient, I can just peg theta to be omega t over 2. And this signifies that all of the bias current goes through the resistor, and the resistor can keep up. This means that the junction is not conducting anything, and it's perfectly insulating. So if I measure the voltage, it increases linearly just with the slope of the resistance of the resistor. If this frequency is above this threshold, then theta cannot keep up in this equation of motion, and it has to slip. And if you then solve this equation of motion, which is a fun exercise, you find this sort of behavior, that you get an average AC and DC component, and the DC component scales inversely with current. Okay, and so this is the breakdown of the Coulomb blockade I mentioned before as a result of that dynamic localization. So this is the VI curve that's predicted classically from this Hamiltonian. Now note specifically that in this regime, the DC current is on the order of lambda squared. Lambda was the transmon bandwidth, which we said is a small parameter. So to emphasize, we can also look at this side of this threshold in a perturbative way and expand in powers of this lambda, which would be our small parameter. So now, the problem with this construction, if you run an experiment, is that we've created a very high impedance transmission line, or like a very high impedance rope. But it has been artificial, and the vacuum is a low impedance medium. And so eventually our experimental system ends somewhere. The fridges are very small. And beyond that is the very large rest of the world, which is very low impedance. And so this would create an impedance mismatch at this interface. You can think of this rope analogy where there's an end to the rope, and at the end of the rope, there's a thicker rope, right? And so this mismatch point will cause reflections of waves traveling up and down. And this means that actually, instead of a single transmission line, what we should think about as capturing experiment is that there's some finite stub with high impedance, and then an effectively infinite rest of the circuit. Say the leads going out of the fridge, right? Your sample in the fridge is, a couple of microns, it's very short, and then you have 2 meters of a coaxial cable for us that's infinite. And you can still capture that if you just make this single impedance frequency dependent. And it will have this resonance structure that essentially corresponds to the standing waves that can occur in the short stub. And so this brings about a dual question. One is, well, now that I have this particular structured impedance, does this affect the conclusion of transitioning into an insulating state? The flip side to this question is, I now have a spectroscopic comb with which I can probe the junction. Can I learn anything new about its insulating state by leveraging these resonances? And indeed, we found that these junctions have sort of been separated and studied separately for their DC response. So people have measured Bloch oscillations in junctions. That's fine. And people have done microwave photon experiments where they analyze, these photons traveling down the transmission line, and when they impinge on the junction, what happens to them. But nobody has really considered them in the same context. So what does the behavior of these photons change if I superimpose a DC current on top of the photons? Or does this IV curve change if the environment has any resonances? And in particular, this work was motivated by a talk I heard in the March meeting now almost 2 years ago, where so Roman at the time here at UMD, he presented this measurement curve they took. So if I grab this figure from literature and I just flip it on this side, you see that it's kind of like the same feature people expect to measure due to these Bloch oscillations. Essentially, it's this downturn. But also, what's up with all these fringes, right? That's what really caught our eyes. And I should say a very strong disclaimer is that our work was motivated by seeing this talk, but we are now modeling. We don't claim to model this experiment, if only because their devices here are kind of far from the regime that we can capture theoretically. They're very far from the transmon limit, etc. But this is what gave us our initial food for thought. And so, again, to emphasize the key takeaway is that if you have a structured impedance with some resonance frequencies, it leads to resonances for certain kinds of your bias currents in various quantities that you can measure. So one would be the voltage current relation. Second is if you apply current, you'll see photons coming out of this transmission line, and there will be peaks due to these resonances in the spectrum of photons. And second, you can send photons in and scatter them off the junction. And the scattering cross-section will also have resonance-like dependence on the current you're using to bias your junction. Any questions so far? Okay. So the way to take a stab at this theoretically is to realize, so our displacement charge theta, it has this decomposition in terms of the eigenmodes, A and A dagger, and the coefficient, this is the H bar over M omega of a quantum oscillator in terms of electrical units. And recall Faraday's law. It means that the voltage is the time derivative of flux across an object. Now, we said that theta is charge, and the conjugate variable to charge is flux, which means that e to the I theta is a translation operator for flux, right? Isn't that cool? And the units here are such that this is exactly a translation by one flux quantum. And so I can compute the voltage across the junction by the rate at which these flux increments occur, right? And so this is just Fermi's golden rule with this cosine perturbation. And you can massage Fermi's golden rule in terms of the Fourier components of a correlation function. And what we find is that it is these vacuum fluctuations and the spectrum of fluctuations of the displacement charge that will determine observable quantities. And so specifically here, see that the voltage is directly proportional up to this coefficient lambda squared to this correlation function, which I'll call C. Now, you can just evaluate this in terms of a constant impedance. Suppose it doesn't have any resonances. And what you find is that the ratio of voltage to current, that would be the resistance of the junction, behaves as this power law. And this power law switches signs precisely when Z equals to RQ. And the difference between the resistance increasing or decreasing with current is the distinction between conductor and insulator. So in this regard, this construction replicates the prediction of quantum phase transition precisely at this point. So well done, us. And now let's turn the crank on the case that there are resonances. So I'll now scare you a bit with a bit of complex analysis, just a brief explanation of how you evaluate these guys. The way to understand this is this corresponds to an integration in the time domain over a complex correlation function that will have some poles. Because this is a 1 + 1 dimensional problems, there's the classical, logarithmically divergent IR poles. And our contribution is that we've added these real frequency poles that correspond to the cavity modes. And what you end up doing is you just do a lot of contour deformations and you isolate your poles. This doesn't really matter. The point is that morally speaking, you can think of Z of omega as sieving out frequencies where it hits a resonance, these omega n. And then I can expand this exponential term by term. And so we find that we need the Fourier transform of a product of pure tones. And the number of products corresponds to this ratio of RQ over Z. So morally speaking, we get nonlinear mode mixings of every possible combination of resonant modes. And so if this is the spectrum of modes in our inverse impedance, because they're equispaced, any combination of these frequencies ends up being the same set of frequencies. And this correlation function just inherits the same positions. And recall this correlation function is essentially the voltage. And what we find is that compared to the case that the impedance was constant, you suck spectral weight into these frequencies. Also, because of this nonlinear mixing, when you excite at a particular frequency, you're never sure how many photons are going to emerge. You can have one photon output, or two, or three, or four with different weights. And this uncertainty in the number of photons that comes out corresponds to the line width of these guys. And so this is a vestige of these logarithmic divergences. We find that these resonances in the voltage curve, they also widen out logarithmically. And finally, the fact that the heights of these resonances are going down, that's a vestige of this Schmidt insulating transition. So now we found out that the voltage will have peaks whenever the Bloch oscillation frequency, which again is basically the current, hits a cavity mode, omega n. I mentioned other quantities. So for example, the emission spectrum, you can also compute it, and you find that it's very similar. It's again given by this correlation function, now evaluated at this frequency difference between your bias frequency and the frequency your detector is tuned to, and also divided by Z of omega. So you'd expect that this one will show peaks whenever either the numerator or denominator have a resonance. So either omega minus small omega is a cavity frequency, or just omega is a cavity frequency. And in particular, I might be able to satisfy these two conditions simultaneously. And then I get what I call a double resonance. So here are like two curves with different parameters where you generically said you have two resonances corresponding to these two conditions, but sometimes these two conditions coincide and suddenly the response goes up. Then I mentioned scattering experiments. So imagine if I send a photon that's actually now very high energy close to the band gap that we neglected before the transmon. The transmon will absorb this photon and spend some time in the excited state, and then decay back and release this photon. But because we are also driving the system with some DC bias current, the emitted photon can actually pick up energy from the bias current and upconvert slightly. And so we might get the higher energy photon than the one we put in. And that's something that cannot happen if the current is set to 0. And if you compute this scattering cross-section, you again find a very familiar form, again, correlation function, impedance, and impedance. Now, of the incoming and outgoing frequencies and the drive frequency. By now, we learned how to play this game, so we know that this will have a peak whenever this combination of frequencies, or the incoming or the outgoing, intersects a cavity mode, or if by any chance all three of them happen to match a cavity. And so just an illustration, but generically, this could be accomplished. So for the spectrum, you can plot it in terms of the excitation frequency and the monitored frequency. And we see two sets of parallel lines. They correspond to those two resonance conditions, and generically they intersect, say at these points. And you can also plot this scattering cross-section. And now you see three sets, like horizontal, vertical, and diagonal, correspond to these three resonance conditions. And for reasons I won't get to, the spacing is not quite constant, and that's good because it guarantees you that somewhere these three conditions can be satisfied simultaneously. So I think, yeah, this point turns out to be the closest to this fine-tuned point. So you can find these points in your parameter space and experiment. OK, so that's the end of the first part. It's a good point to stop for questions.
Yeah, also in terms of time, we have like 5 minutes or so left.
Oh, 5 minutes. Oh, OK. I'll blitz through this then. It's a shorter part. So our point was that you can think of this as a way to maybe generate frequencies on chip, right? I put some current that I control with a power supply, and on the chip, it'll generate photons given by this emission spectrum. But you're also going to get a lot of harmonics, and if I don't look at the width of these peaks, but rather at the width in which these peaks fall off, this is a quite broadband spectrum, so it's not so good as a frequency generator. So can you actually make this emission much sharper? And the answer is yes. How about you lock it to an external drive? So in this section, my external current bias is not just DC, it also has a small AC component. And so our Hamiltonian now picks up this extra AC term inside the argument to the cosine. And what you can do is you can actually bring the effective Bloch frequency that's controlled by the DC component into a resonance with your external AC component. And so the condition for that is that the Bloch oscillation frequency is some harmonic of the external one. And if you then expand around this effective point, you get an effective Hamiltonian with two differences. One is it's as before, but now you're sensitive to the difference between the two frequencies, and you slightly change your coupling constant, which doesn't really matter. And so the point is that you find that close to these resonance frequencies, you get replica behaviors. So they're essentially the same as the behavior when the bias current was exactly 0. So if you recall our classical VI curve, if I now add this AC component, I'm going to get these replicas at extra frequencies. And actually, we realize, hold on, this starts to look like a current standard, which is very apt if you think about quantum metrology these days. So I've said our device is kind of dual to regular Josephson junction. And the Josephson junction is these days the golden standard for voltage references. So the point is that with the AC Josephson effect, if I know how to generate a very accurate frequency, I can generate a very accurate voltage. The way this happens is through the same mechanism where you get these replica staircases in voltages on a regular Josephson junction, right? And so we want to accomplish the same task now with Bloch oscillations and a current reference. But now, to be a good current reference, you want these slopes to be as close to vertical, right? Otherwise, where exactly is the reference? But if we want to make the slope close to vertical, I want to increase the resistance I'm shunting the junction. But if you increase the resistance, what we claim is that it also causes broadening. So this is a classical IV curve. And as I said before, quantum mechanically, we so far only access this decreasing slope. And quantum mechanically, actually, this point will be sharpened. And the question is, can we treat this region, which we couldn't access before because it wasn't perturbative in this parameter lambda? And specifically, how sharp could we make these transitions? And so, as I said, the issue so far is we looked at large biases, which were perturbative in this Bloch bandwidth lambda. The problem is that lambda is RG relevant. This means if you probe physics at lower frequencies, the lower you go, the larger lambda flows. And eventually, it's just too big to have any meaningful senses of perturbation. Instead, what you can use is that there's an exact duality between this system and itself between weak and strong coupling. So if I essentially map voltage to current, current to voltage, and charge to phase, there's an exact duality between this Hamiltonian and this Hamiltonian with a prescribed relationship in the coupling constants. And the difference is that if here the impedance is very large, here the dual impedance is actually very small. So this means before we calculated this side of the IV curve and found this power law, in case there aren't any resonances in this part of the talk, then by duality, we find the power law that happens in this part. And this is the broadening I mentioned before, where you have to have some sort of smooth crossover quantum mechanically here. And with the replicas, this is the IV curve you expect with an external drive. And we have expressions for this broadening. So what we find is that to get sharpness that is comparable to what people use in voltage standards, you need resistance that's roughly 20 times the quantum. Now, the thing is that this is something that's quite difficult to accomplish in this Josephson junction arrays. You can maybe reach 3 or 5, but 20 is hard. So people measure these Shapiro steps in these Josephson junction arrays, but they're not very sharp. But when people make experiments in devices with 20 resistance quantum, here they just slap the regular resistor there. Things seem too fuzzy and not sharp. And so it's important, and that's part of our outlook to understand why this happens. And so this, for example, could be due to the heating that the regular resistor induces in the system that might overpower the quantum broadening. So I'll wrap up with a few open questions. So one is we made a few charitable assumptions when we modeled our waveguide. For one, we assumed a nonlinear dispersion of a waveguide. So say that the velocity in the waveguide is constant. That's generally speaking not true. As you can tell from this experimental plot, that this is the mode spacing, and it changes quite a lot over frequency. And this will have the effect of actually leading to a further broadening of the resonances we predict. Secondly, the transmission line itself is also a source of loss, right? This is this guy. And that's another thing that needs to be included in a more realistic model. Second, we can consider regimes towards stronger fluctuations. So if I haven't mentioned, here we considered impedances that are over the critical point of R cube, but way over the critical point. So you're deep in the insulating regime because that's sensible to expand around perturbatively. But as you go closer to the actual point, these multiphoton processes become more dominant. You can get extremely high order processes. I think this promotes the role of actually low frequency fluctuations, because essentially you can almost for free break a photon that has energy of 1 to 2 that have 99% and 1%, and that costs you essentially nothing in terms of the order of the process. And so it's interesting to think about how these showers of low energy photons affect the theory. Second, you can think of limits as you crank the resonances in your impedance function to be sharper and sharper. Because on resonance, you get very effective photon production in that spectral function. What happens if you produce too many photons? Do you get heating then? Can you achieve some sort of steady state? This was, to me, kind of felt similar to what people have now demonstrated in literature, where you can get lasing out of Josephson junction. So that's another interesting regime to think about. And lastly, to sort of circumvent this problem I listed before, maybe you can cook up a hybrid device that has the resistance implemented both by a regular resistor and these transmission lines. So imagine a long transmission line matched with a resistor at its end. So if the resistor creates any heating, it's far enough from your Josephson junction so that the heating doesn't affect it. That's, again, a subject for further work. So to summarize, these high impedance Josephson junction array superinductors opened this door to strong coupling circuit QED. Maybe the one takeaway I would like you to remember is that these shunted transmons within a quantum mechanical description essentially give you a device that's dual to a Josephson junction. And with DC drive, you can induce these Bloch oscillations, which lead to a plethora of these interesting experimentally measurable quantities. So the VI curve, the photons, radiation spectrum, inelastic scattering cross-section, and these quantization, I forgot to mention names, Shapiro steps with applications to metrology. And yeah, that's the end of my talk, and I'll be happy to take your questions.
All right, thank you. Any questions from the audience? I can get started with one. So maybe I missed it, but in the beginning you were talking about this insulating phase, which is under debate. So what does your work have to say about this debate?
So our work kind of falls on the side of there is a transition. I should say that the debate actually has two sub-debates. So there's the bigger one about whether the transition happens at all. That's a bit more fringe. I think now there's more of a consensus that the transition is a thing. Then there's a sub-debate which claims, let's see, the laser pointer doesn't want to scroll all too well. Okay, instead of scrolling, I'll just say, so I've mentioned that this transition point happens when this ambient impedance matches the resistance quantum, right? And the debate is whether this point is actually independent of the circuit parameters. So there's some conflicting literature early on that says that actually, depending on if you have a junction with a certain EJ and EC, the critical point will also depend on EJ and EC, like what's the exact value of impedance you need to hit. And it's not a universal constant RQ like I've illustrated here. I think now also in the last couple of years or even months, there's like increasing theoretical work kind of establishing on firmer and firmer footing that the original prediction that it's actually a universal constant is true. So that's roughly the state of the literature as I understand it, that it's still not complete consensus, but it seems to be approaching that.
All right. Other questions? All right. If not, let's thank the speaker again.
All right, thanks for having me.
Thank you.